Okay, let's start chapter 15, which is on intraseasonal variability in the tropical atmosphere. So there are intraseasonal variabilities in the ocean as well, and they are of course responses to the intraseasonal variability in the atmosphere, but there are also instabilities in the ocean, like the tropical instability waves, which can be manifest at those time scales as well. Billy Kessler and Harry Hendon have nice chapters in a book on intraseasonal variability by Bill Lau and Wayne Walliser, the last edition of which was published in 2012, that you can look up. We have already mentioned intraseasonal variability at several times in the previous chapters. In chapter 8 we looked at this, and as well as in chapter 1 as introductions. So this is the classic Madden-Julian original depiction of the Madden-Julian oscillation, which is going across from the African sector, across in the Indian Ocean, into Indonesia, across the Pacific, into South America, and so on. So you have these phases. You can think of convective phase here with converging motion, deep clouds, deep convection, all the way into the upper troposphere, creating cyclonic circulation, low sea level pressure. Ahead of it has part of the MJO itself, which creates subsidence and high pressure, the weak winds, divergence at the surface, warming, which kind of is a self-induction or a self-reinforcement mechanism, but you can see how the waves propagate the sea level signal ahead of the convection and behind the convection, and then the convection has a way of propagating eastward and decaying, especially as it gets into the eastern Pacific, where the sea surface temperatures are cold. It cannot support convection. We can also look at it as we did in I think chapter 8 maybe, composite structure of the MJO in terms of the OLR and 850 hectopascal wind speeds. So we are looking at intraseasonal anomalies. So where there are negative colors, we have low OLR, so convective phase. Ahead of it you have weak winds, which favors reduced loss of latent heat, and warming of SST has high OLR, dry phase, subsidence, and the convection moves eastward. There are various issues associated with how the convection actually crosses the equator across the maritime continent, which we will come to later on. And you can see the reappearance of the dry phase behind, which reorganizes the sea surface temperature, creates the vertical temperature gradient between the sea surface and something like 200 hectopascal, which we will see, which is an indication of the moist static energy gradient and buildup of the convective available potential energy, which then gets converted into kinetic energy as convection, and then the next phase starts. So that's kind of the basic idea of this eastward propagation. Of course, this is a boreal winter phenomenon, goes mostly from October to April, and in May to September the Indian Ocean region has the Indian summer monsoon, and then you have northward propagating systems which are called the monsoon intraseasonal oscillations, which we will look at in the next chapter when we come to the monsoons. So here we will just focus on these eastward propagating features. Well, to look at the frequency wave number of the MJOs, we used the satellite cloud top temperature spectrum and looked at the westward propagating inertial gravity waves, equatorial Rossby waves, long ones, Kelvin waves at various equivalent depths, and then we noted that the MJO actually sits down here much slower propagation and frequency down here at 30 to 60 days, low frequency compared to these. And we had talked about the Kelvin and Rossby structure in the Mjos as well, which we will visit again briefly in this chapter as well. The genesis of the Mjos, which is discussed a lot in literature, typically tends to happen over here, but in the western Indian Ocean, which is favorable for warming, as we will see later on again in terms of SSTs, especially also because the winds are typically very weak, as you can see here. But the seasonal variability of the basic state is very critical, because Mjos are propagating through this strongly varying basic state at seasonal and interannual timescales in terms of El Nino, Indian Ocean dipole, the Atlantic Nino mode, and so on that we talked about previously. We will see that there are what are called circumnavigating Mjos, so they seem to lose the convection signature over here because the sea surface temperatures here are cold, as I said, but the geopotential and other velocity signatures do propagate across in some cases, and there are some ideas that maybe they cross over Africa and get reignited or recharged over here, but there is also evidence that the extratropical perturbations are needed to create convection. We had talked about the westerly duct and the upper tropospheric trough as continuous exchange of the extratropical signatures with the tropics, but we should mention here, and then we'll mention again later, that this region seems to have plenty of extratropical perturbations coming in from the southern hemisphere that are associated with triggering Mjos, or so-called Mjogenesis. The variance in OLR we looked at for boreal summer and boreal winter months. Obviously, boreal summer is dominated by the monsoons, South Asian and the East Asian monsoons, and you can see the high variance at the the synoptic time scale of 2 to 10 days, quasi-biweekly time scale, and what we are calling here the intraseasonal variability, 20 to 60 days. Some people refer to this as high frequency intraseasonal variability, this as low frequency intraseasonal variability. And we will see that even the low frequency variability of the basic state actually modifies the background SSTs, zonal stretching that we talked about, and of course the tropical, extratropical connections and so on, which would impact the intraseasonal variability in terms of their propagations and interactions with the basic state. DJF, obviously the ITCZ has shifted further south. You can see it's further north here and stronger, weaker here, but SPCZ is stronger here, more extensive than down here, especially in the 10 to 20 day and the 20 to 60 day band, and this is the Mjo season, typically from October to April, as I said, that we will focus on. Okay, there are what are called boreal summer intraseasonal oscillations, which are also called the monsoon intraseasonal oscillations, but also signals propagating from the western Pacific northwestward into the Indian Ocean across the South China Sea, Bay of Bengal, and so on and so forth, which we will see in the monsoon chapter, chapter 16. Okay. That's kind of the setup of the Mjos, even though we are calling it tropical intraseasonal variability, because as we will see, Mjo is not a monolithic thing. There are various different manifestations of intraseasonal variability during the boreal winter season. Not all are Mjos. Okay.